Hi, all, and welcome to the Medical AI Lab Talk series. I'm delighted that today we have Viet Vu presenting InstructGPT. Looking forward to your talk, Viet. Take it away.
Okay. Hi guys, I'm Viet, and today I'll be talking about InstructGPT that comes from a paper by OpenAI on training language models to follow instructions with human feedback. This is actually fun. So the content that we're going through today, first part is the background, the landscape of language models right now. The second part will be the main ideas of InstructGPT, and the third part will be the notable results and limitations. So yeah, we are having a lot of advancement on the front of language models right now. There's an emergence of many different language models with larger and larger architectures. So you guys must have heard of BERT and all its variants. So it started out with 345 million parameters. And since then, we also have like GPT-2 and GPT-3 with about like 1.5 million. And then since then, it's just like increase and increase. And now we have like the latest model right now, which is like Switch C, which has like 1.6 trillion parameters. And these language models are trying to of course, like trying to beat the state of the art benchmark on predicting tokens on a sequence of text. Yeah, but the problem we are trying to consider, I guess, in this problem is more of like on the natural language understanding side. In their paper, BERT is claimed to tackle this problem. Like unsupervised pre-training is an integral part of many language understanding systems. But the main critic to this claim, according to Bender et al., is that like this claim might not hold true due to the part that like the meaning of the sequence of text in the training data is not encoded. So the first one is that like there are manipulations of the test data that could remove spurious cues, so it makes easier for the model to to have good results. And the second part is that the training data only has semantic forms, which is like a part of language, but it doesn't encode like actual meaning. And so the fact that it performs well on like the NLU, I guess like statistics, it's not like it's more of like what's it called, an indirect effect rather than the fact that it's like directly addressed in the training process. And so we have the main problem here, which is like there is a misalignment with the user's objective. Where it's like the thing with like most language models right now we have is that like it's trying to predict the next token based on an input sequence of text. But somehow the user's objective is not like exclusive to that. It's more like user may want to get information about a particular concept, and while the model having that very narrow kind of target is not likely to give the most helpful or truthful answer. And this is why user feedback is so important. We want to build language models that could benefit humans in their I guess like subjective goals. And so this is what like OpenAI came up with, which is called like InstructGPT. And so the very high level criteria of InstructGPT are helpfulness, honesty, and harmlessness. So helpful is that the model helps the user complete the task. Honest in that the model should not make up information and mislead the user. Harmless in that the model should not cause psychological, physical, or social harm to the user. And so these targets are great. Of course, this is what we want, but the main problem is that I guess the hard part is that like these criteria are very human subjective. And so how do you like encode this to like, an algorithm or a paradigm to train and to evaluate? And so the general solution is to use human feedback in order to to train some kind of like a reward that signals the neural network that like, oh, this is the expected behavior that you should go for. This is like the high level details of this model, I guess. Yeah, so just before we begin diving into the model's details, in the paper, which is the paper they released, training on human feedback, there is a link to OpenAI Playground, which is like an interface, like web interface, where you can just put like a description, and then there will be like you can push the button generate, and then the model will generate like a sequence of text for you. Like for example, here I put in like describe machine learning, and there is like the output like below is what InstructGPT gave me as like an answer. Okay, so now we dive to the main ideas of the model. There are 3 steps that we see here. The first one is to collect demonstration data and train a supervised policy on that demonstration data. The second is that we collect comparison data and train a reward model. And step 3, which is the last step, is to use that reward model to fine tune the policy we have in step 1 in order to have a policy that's more attuned towards like users' instructions. Yeah, so we're gonna dive into like each step right now and what it does and like how does it like correlate with like the goals that we set in the beginning of the presentation. So step 1 is to collect demonstration data and train a supervised policy. And what do I mean by demonstration data? This data human labelers put sample answers as like desired output behavior. A data set is curated from this and then used to train on GPT-3, which is like the latest model like before that of OpenAI, and use supervised learning to train a supervised policy. The sources that we get the outputs like demonstrations from are like labeler written. There's also that API which I mentioned earlier, OpenAI Playground. It was also used for like a selected set of like labelers that can like put in their prompts, I guess, and their sample answers for that. The size of this data set is around like 13,000 training prompts. And so the number of human labelers, like as I've read in a paper, around 40. So an example of a demonstration data can be seen here. So the prompt would be something like explain the moon landing to a 6-year-old. And when the labeler says that, oh, demonstrates the desired output behavior, we something like, oh, some people went to the moon. And this data is used to fine tune GPT-3 with supervised learning. And so, so this is the first step. Like we have accomplished the first step of encoding at least some human opinion in what is good output into training the model. However, like as the model is probabilistic, it is a generation problem. So the model policy might still output text that is not very user attentive. This is like an empirical observation, I think, in the model evaluations. So how we train even more towards this goal? So the general solution is that when you have different outputs of the model, what human labelers can do is they can use a rating system or reward system. A rating system is that you have different outputs and the labeler can rank them on how desirable they are. So if you go back to this slide, here we have explained the moon landing to a 6-year-old. And then there are a few outputs, A, B, C, and D, as you can see here. Explain gravity, explain war, moon is natural satellite of, and people went to the moon. And we can see that like people went to the moon is like the most like desirable answer. And then comes the moon is a natural satellite of. And explain gravity and explain war, which is like not really related, will be ranked not really well. And the main gist of this thing is that we can train a reward system so that like better outputs will be given like higher rewards. So we can dive more into this by looking a little bit more into the details, the technical parts. So the first step is that the labeler ranks outputs for a given input. One input, you have a ranks of like different outputs. And the rankings are used as true labels. It's just kind of like a self-supervised like training thing when you have like labels and then you try to recognize a reward system where the rewards of the most desirable ones will be higher. And so we minimize a loss function that maximizes the difference in reward between the correct output and other outputs. And so the function is as below, right? It's like the negative average of all the log softmax of the differences in reward. So I guess like this is a lot of details in the loss function, I guess, but the main intuition that we have in the loss function here is that when you have a large difference in reward between the correct output, between the more desirable output from the less desirable output, when there is a large difference in reward, it leads to higher logistic values, which is like one-dimensional case of a softmax function. And when applied to the negative log function, will give positive values because logistic values are always less than 1. So in the end, we will have positive values that are very close to 0. If this is like, this is a desirable place, and then we have loss close to 0. And when the loss is great, it means that the rewards are close to each other, which is like not what we want. We want like a very like differential reward system, essentially. And here we can use reinforcement learning to train a policy that maximizes reward. So at the end of step 2, what we have is a reward model that can, for each output, it expects a response. And when you input a response into the reward model, it will give you back the reward as an output. And then we can use like a very like commonplace reinforcement learning setting with like the bandit environment, where like the bandit here is the model, is the reward model. And when there is an input, it expects a response. And if you put an response to that, it will give you back a reward. And the question here is that, like, suppose that we are an agent, right? And we want to train a policy where like we want to maximize the reward. And here in the paper, they use an optimization algorithm called the proximal policy optimization. And the significance of this algorithm is that like, once we have this policy, we can fine tune the supervised policy in step 1 with human assigned rewards. So below is the objective function that we were trying to optimize in the model. No need to spend too much like attention to the details. It's just that like, let me see my arrow. This thing right here is the reward of a pair of input and output. And so it gives you a reward. Of course, we want to maximize that. And here, the log term is a callback library divergence between the policy, the reinforcement learning, and the policy, the supervised policy at the end of step 1. This is a penalty term. That's why there's the minus sign. We don't, of course, like we wanted to change a little bit, but we don't want our reinforcement learning policy to deviate too far from the supervised fine-tuning policy. That's why there's a minus sign. There's a minus sign before the callback library term, so that it's more like a callback library penalty. And here in the model, they are also trying to propagate pre-training gradients in this objective. So in the model, they're gonna like set like, a controlling term with gamma here, whereas they trying to control, like maximize the log of the policy distribution, the reinforcement learning distribution, but with respect to the pre-training distribution. So the average is with respect to the pre-training, so that they can propagate the pre-training weights there in order to prevent. So the main idea is to prevent the model from overfitting to the reward system. You still want to follow, like, you still want to control the deviation from the supervised policy in step 1. And yeah, so coming back to the evaluations, the model is trained, And we have the very high level criteria of helpfulness, honesty, and harmlessness. And of course, if we train by user input, we should also evaluate by user input. And so we evaluate by selecting prompts from labelers that are not included in the training phase, so that they judge of course, like the labelers that are included in the training phase, they will have their own judgments, and we don't want to overfit to that. So as like a test set, we're going to evaluate by selecting prompts from labelers that are not involved in the training phase. So for helpfulness, we can only depend on labeler judgment, because like helpfulness to humans, right? So like we're trying to see whether it's helpful to the labeler's judgment or not. So we evaluate the model's policy to follow explicit instructions and also to infer instructions. For helpfulness, we also use labeler judgment to evaluate the model's tendency to make up information on closed domain tasks. Closed domain as in like, it's clear what the model needs to tackle, and then when it doesn't, then we say that it makes up information. We also evaluate benchmarks on the truthful question and answer data set. For harmlessness, we have labelers evaluate whether the output of the model is appropriate or not, whether it denigrates a protected class or contains derogatory content. And we also benchmark the model on the bias and toxicity data sets, which are like named here: real toxicity prompts and crowd escape. So now we go into results. The first result is that we can use labeler judgment. So at the end of the first step of the model, we have what's called as a supervised fine-tuned model, or abbreviated as the SFT model. It has like 175 billion parameters, maximal size. And so what we're trying to do is that we're trying to compare the output of the model at the end of step 3, which is called PPO-PTX in red here, compare to how the SFT does, and also compare the performance of the GPT on the criteria that we mentioned in the evaluation. And looking at this plot, we can totally see that like the win rate against the baseline SFT model is very low for GPT, which means that like in most cases, you can see that like the human labelers prefer the outputs of the supervised fine-tuned model. Even then, was like much more than what GPT-3 could do. And after the second and third step, when we incorporate the reward system, we can see that the win rate gets even higher than the supervised fine-tuning. So we can see here that improves a little bit from the green line. Note that like for the green line, the N dot is always at 50% because the green line belongs to the SFT model. So as 175 parameters, it's the exact same model. So that's why we have to put it at 50%. But for the PPO-PTX model, we can totally see that like it performs the best on the win rate against the model at the end of step 1. The results are also like split. Like they are differentiating between the held out workers, which is the labelers that are not included in the training phase, and the training workers, who are included in the training phase, to prove a point that like, we're not overfitting to the judgment of the human labelers, which was like central to the argument that we're making. So we also define hallucination as the phenomenon that the model outputs made up information. It's called the model hallucination. We also like trying to evaluate the ratings across different criteria. Attempts correct instruction, follows explicit constraints, hallucinations, and uses language appropriate for customer assistant. And so the red column that we have here is the model at the end of step 3. And the darker blue color belongs to the GPT-3 model. We can see like how much it improves. It attempts correct instruction better. It follows explicit constraints better. It has less hallucinations. So here we can say that 42% of prompts for GPT is like more like made up information compared to PPO-PTX. And it also contains like language that are more appropriate for customer assistant. And lastly, we present results on the truthfulness and informativeness with respect to number of parameters. As we can see here that we evaluate on the truthful QA dataset. And this instruction is like more like human labeler, like judgment on how truthful it is or how made up the information is. So when you look at this, it is clear that like the trend of making models that are more massive are not necessarily aligning with like the user's objectives that we present here as like being helpful, being truthful, and being harmless. As with like the model PPO PTX on the truthful QA dataset, we see that when it has like 6 billion parameters, it performs better than when it has 175 billion parameters. So this is a thing that like Bender in his paper talked about, like massive LMs that are not like, you know, like aligning with like the natural language understanding front might not be the way to go in certain domains, of course. And so, of course, like the model has some limitations. First of all, in methodology, is that like the human labelers, of course, like we're using human input, and then that is like, you know, it's biased in a very intricate way. So the human labelers might not be representatives of cultural backgrounds, beliefs, or personal histories, and hence the ratings and demonstrations might be biased. But they are very central in the training of the model in that they provide, first of all, demonstration data, second, output rankings, and they also evaluate how good the model does. And as with performance, the model produces non-desirable output when there is no explicit prompting. So what do I mean by explicit prompting? It's, for example, if you tell the model to explain like, oh, like what is the moon, for example, then they will provide output that's related to that. But when there's no explicit prompting of like what to do, that there is like a tendency to produce output that is sometimes like harmful or like contain like derogatory content. So that is what like they said in the paper that like they're gonna work more on that in the future. Yeah, so that is the end of my presentation. Thank you like so much for listening. This is like a very fascinating paper, and also encourage you guys to try out the OpenAI playground if you have some time to see how it does. It's very interesting.
Thank you for the presentation.